Okay, today's data structure that we're going to talk about is called a graph. So when it's important to highlight relationships, a visual representation is often very useful. And a graph represents relationships between items. So for example, when you think about registering for classes, you look at a list of courses that are available and the prerequisites that are required before you can take that course. If you were planning to earn an entire computer science degree, for example, you might see a list of courses like this and their prerequisites. Okay. Although this list has all the data, it's hard to visualize or make a plan out of this list. Okay. It would be nice to somehow see the courses that you would want to take. Okay, so if one could see these courses and the relationships between them, it might be easier to see a logical path through the degree. Okay, so I'm going to take this data here and just kind of draw it like this, where there's really kind of a path through the series of courses. So in other words, if you want to take CS 102, well, you first have to have had CS 101 and Math 102. Those are the prerequisites for CS 102. So this picture, I think, provides, gives you a good sense of what has to happen for you to earn this degree. I think it's much more intuitive than just the list. Okay, so this is a graph, and the items in a graph are called vertices. Okay, and the relationships are called edges. So a graph is really just a collection of vertices, which are the data, okay, or the things that we're storing, and the edges are the relationships between them. So you might also see something like this in a math book. A graph is just a collection of vertices and edges. A graph can be directed, in which case it's called a digraph, or undirected. So this is an example of a directed graph because the relationships are one way. If there were two arrowheads on each line here, or if there were no arrowheads at all, that would make it an undirected graph, and you could flow in either direction. But this directed graph, there's definitely a direction that you must take these courses. So graph theory comes from a branch of mathematics called discrete math. And let's look at another graph here. Okay, so here we have a graph with 5 vertices. So the vertices are labeled 0 through 4. And then we kind of use this absolute value notation to count how many vertices there are. So the V inside the bars here equal to 5 means there's 5 vertices. The edges are usually listed like this, where we have kind of a set of pairs of numbers between the vertices. So from 0 to 1, that's an edge. And from 0 to 3, well, that's another. 0 to 4, 1 to 2, 1 to 4, and 2 to 4 are all the edges. And there are 6 edges in this particular graph. Okay, when we talk about graphs, there's usually 2 main questions that we ask when we're using a graph. We ask about these things called neighbor queries. So for a given vertex, find all the neighbors. And edge queries is a question like, is there an edge between vertex X and Y? Okay, so let's go back to the picture here for a second. If we were to do a neighbor query on this vertex 0, that's saying, tell me all the neighbors. Well, the neighbors, the directly connected neighbors are 1, 4, and 3. And then an edge query would be something like, is there a direct connection between 2 and 3? So in that case, that would be false. If we said, is there an edge between 2 and 4, that would tell us, yes, that's true. Okay, so we are going to talk about how to create a graph, okay, in code. The first representation that we'll look at is called an adjacency list graph. And in this graph, you store the vertices in an array-based container, like a safe array or maybe even a hash table. But then you have a mirrored safe array of linked lists that hold pointers to the neighbors. Okay, so this is an adjacency list graph. Now this is still a container, so this collection called vertices, like I said, it's either a safe array or a hash table, and it holds data, right? Because all of our containers hold data. But then we have this mirrored safe array. Okay, so there are 6 elements here. There are going to be 6 elements here with the same index values. Okay, but what we're going to store here are linked lists. This is kind of similar to our hash table. So what we do in here is we put pointers to all the neighbors. So for example, here at index 1 we have a vertex, and then if we go to the neighbors safe array at position 1, there's this linked list, and if we follow through here, we will see we can follow pointers to that one's neighbors. So this might be a pointer to this one might be a pointer to this piece of data over here. Okay, so with this type of graph, an adjacency list graph, neighbor queries are very efficient. So all you have to do is find the position of the item in the array. Right, so let's say again we want to find all the neighbors of this vertex at position 1. We just go to the neighbor safe array over here, and we get this linked list, and we basically have a collection of neighbors. We can just march through and grab those neighbors. Edge queries are somewhat inefficient, okay, because you have to look through all the neighbors in the linked list to find if there really is an edge between 2 vertices. Right, so if I wanted to know, is there an edge between vertex 1 and 2? Well, I'd first have to find vertex 1 and then find the linked list and start marching through here and saying, well, are you vertex 2? Are you vertex 2? So there's a little bit more work involved with an edge query if you use an adjacency list graph. But they're really great for neighbor queries. It's very efficient to just go grab all the neighbors of a vertex. Now there's another implementation called an adjacency matrix, okay, which again has a collection of objects, the vertices. But then the way we represent the relationships is we create this 2-dimensional collection of numbers. Okay, where if there's a 0 in one of these spots, that means there's no connection from this vertex to this one. So there's always a from and a to. Okay, so if I wanted to say, is there a connection from 2 to 3? I'd go to row 2, column 3, and a 0 means that those two vertices are not connected. If it's greater than 0, well then we know there is a connection between those two. Okay, in this type of graph, edge queries are very efficient. So once you know the x and y position of the 2 elements, you simply look them up in this 2-dimensional array to see if there's a non-zero value. So again, if I want to know, is there a connection between vertex 4 and 2, I go to row 4, column 2, and if that's a 0, that means there's no connection. If it's non-zero, that means there is a connection, okay, or there is an edge. Neighbor queries are somewhat inefficient because you have to march through an entire column of values and look for non-zero values and then grab all the vertices at those positions. So again, if you want to say, well, what are the neighbors of vertex 2, you basically have to march through this column, and anywhere there's a non-zero value, you'd have to that would indicate that whatever row number you're on, that is a neighbor, and you have to kind of build up this list of neighbors. So it's a little bit more work than than the adjacency list graph. So these really complement each other very well. If you need really fast neighbor queries, you'd use an adjacency list graph. If you need really fast edge queries, you'd use an adjacency matrix graph. Okay, this is a container, and the container can grow dynamically, of course. And what that means is your two-dimensional array would have to grow dynamically as well. So in order to make a two-dimensional array dynamically, what you're going to need is a set of pointers to pointers. And then, of course, we'll use the heap to store our dynamic memory. Okay, so let's take a look at this little bit of code here. I have this piece of data called two-dimensional array, and notice the syntax here. This is a int pointer pointer, or the way I like to read it is it's a pointer to an int called two-dimensional array. Okay, and what I'm going to do is remember the way we use the heap is we always create a pointer to the type that we want to store. So what this tells me is we want to store an array of int pointers on the heap, and in order to do that we need to create a pointer to an int pointer. Okay, and that's actually what we do on the next step here. This says two-dimensional array is going to hold the address of an array of x int pointers that are all right next to each other, and the address of the very first one is going to be stored inside two-dimensional array, and that's why we needed a pointer to an int pointer. Okay, so maybe a picture will help us understand here. Okay, so this is the array of int pointers. Remember, with an individual int pointer, we can make that point to an array of ints, and that's our goal here. Is we have the kind of the outer array of int pointers that eventually is going to point to individual arrays of integers, and that's how we build two-dimensional arrays dynamically. Okay, so let's go back to the code here. At this point, we have two-dimensional array created. Now the next step is to build all these individual arrays. So we'll do that in a loop here. So two-dimensional array at position I is going to go from 0 to x. And since each one of these is an int pointer, it can hold the address of an entire int array. So we'll go to the heap and ask for a new array of x integers, and what's going to be returned is the address of the very first one, and the address of the very first integer needs to be stored in an int pointer, and that's exactly what two-dimensional array at position I is. Okay, so this is an int pointer. It can hold the address of the very first one of these integers in the overall array. Okay, the good news is after you kind of wrap your brain around this and you create the two-dimensional array, you can go back to thinking about how we've always thought about two-dimensional arrays, and we can use the exact same syntax. So if we wanted to zero out all the values, for example, we just say two-dimensional array at this row and this column, and we can store the value 0 there. Okay, so that's how you'd create a dynamic two-dimensional array of integers. Let's see what else we can do with a graph. Okay, so here's our summary of the adjacency list graph versus adjacency matrix graph. The adjacency list, we have this array of edges and an array of linked lists that hold pointers to neighbors. Okay, so actually I think this is supposed to say an array of vertices. Okay, so we have the array of vertices and the array of linked lists that hold the pointers to the neighbors. Okay, and then the adjacency matrix graph, we have a two-dimensional array of integers with what I call weights, where 0 means there's no connection and a greater than 0 value means there is a connection. Okay, one other thing we can do with a graph. is we can apply this algorithm called a top sort algorithm. So a graph defines relationships. That's the big difference between this container and others. Each relationship defines something called a partial order. And a partial ordering is just a small subset of the total order in a graph. So for example, the prerequisite of CS 101 and Math 201, which are required to take CS 102, they define a partial order of the courses you must take in order to take CS 102. Okay, so we could kind of draw a partial order like this. This comes from the other picture. So we have Math 201, CS 101. Those are both required before you can take CS 102. Okay, so this is not the entire graph, but this is one small part of it, and we call that a partial order. Okay, the total order is the collection of all the partial orders that make up the graph. So the top sort algorithm says, given a set of partial orders, find at least one total order that doesn't violate any of the partial orders. Okay, in other words, given a set of prerequisite courses, find a sequence of courses that allow you to complete the major. Okay. Now, if we wanted to do this, apply this top sort algorithm to a graph, we can't have any circuits in the graph. Okay, those aren't allowed if you want to do top sort. Okay, so let's look at a graph that doesn't have any circuits in it. Okay, so we have this graph here. This is a directed graph. Notice the arrowheads. Okay, we have 5 vertices, 0 through 4. It looks like we have 4 edges. Okay, and we know some things about the total order of this graph. Okay, we know about the partial orders, and the sum of the partial orders make up the total order. So what this says is 0 must come before 2. If you're going to, kind of visit each one of these elements, well, we have to process 0 before we can process 2. Just like if these were courses, you'd have to take this course before you take that one. And we also know that 2 must come before 4. Okay. Therefore, 0 must come before 4. These are transitive relationships. So one possible way to visit all the vertices without violating any partial order would be to visit vertex 0, right? And then we could visit vertex 1, and then we could visit vertex 2, 3, and 4. So notice if we visit or process each one of these vertices in this order, we won't violate any partial order, right? Because 0 is kind of special because it doesn't have any edges coming into it. So we can do that one without violating any partial orders. 1 is similar. It has no incoming edges, so we can process that one next. 2 does have an edge coming in, so as long as we've processed vertex 0, 2 is a viable next candidate. 3 is fine because we've already processed 0, and 4 is okay because we've already processed 1 and 2. Okay, this is not the only total order, though. We could also have traversed or visited all the nodes in this order: 0, 2, 3, 1, 4. Again, 0, we don't violate any partial order there. 2, as long as we do 0 first, that's fine. 3, we've already processed 0. 1, and then 4 must come last in this case. Okay, so that's another total order. There usually are multiple total orders that can be made, and top sort just says find one of them. Okay, so the algorithm what we do is we label the vertices on the graph so that if there's an edge between A and B, A's label is less than B. So basically, these are the labels that I have created, and the order matters. So if a vertex has no edges coming in, it doesn't need to come after any other vertex. Okay, so that's going to be a special case. And the top sort algorithm basically says pick a vertex with no incoming edges and give it a label. Okay, so that's what we did. And in both cases here, I just picked 0 because 0 had no incoming edges. So I gave it a label. Then for that vertex, you're going to remove all of the outgoing edges. Okay, and then we're going to repeat the process. So let's do that. Let me turn my eraser on here. Okay, so the algorithm says pick a vertex with no incoming edges and give it a label. So this time I'm going to do it in a slightly different order. So vertex 1 has no incoming edges. So I'm going to select that, and I'm going to erase all of the outgoing edges. Okay, so I selected 1. Selected 1. I erased the outgoing edges. Now I'm going to basically repeat the process. I have to find another vertex that has no incoming edges. Well, 4 still has an incoming edge, 2 has an incoming edge, 3 has an incoming edge. Really the only other choice I have now is 0. So I'm going to select that one. And then I'm going to remove all of its outgoing edges. Okay, so here's an outgoing edge of 0. Here's another one. Okay, now I'm going to repeat the process. So I've already handled this one, and I've handled this one. So now I have 2 vertices that have no incoming edges, 2 and 3. So I can pick any order, doesn't matter. I'll just pick 3. I've processed it. There are no outgoing edges, so there's nothing really for me to delete. Then I'm going to repeat. There's only one vertex that has no incoming edges. That's 2. And then I'm going to erase the outgoing edges. Okay. And then I'm going to repeat. There's only one vertex left. Okay. I'm going to get rid of the outgoing edges, and we will have processed all of the nodes. We will have visited all the nodes in an order that doesn't violate any of the partial orders. So this is yet another total order. Now we could do the same thing with our courses. Okay, so this is if you ever meet with your advisor, especially as a freshman, you might kind of come up with a plan for how to get through a major. Okay, and what we can do is just apply the top sort algorithm. So we say pick a course that has no incoming edges, of which there are 2. There's the CS 101 and Math 101. So it doesn't matter which one you take first, since neither of them have prereqs. Okay, so I'm going to pick one. Okay, and then I'm going to erase all the outgoing edges. Okay, and I'm going to store the label CS 101. Okay, then I'm going to repeat the process. I'm going to pick another vertex that has no incoming edges. Okay, and it looks like we're kind of stuck here. There's only one vertex that has no incoming edges that we haven't processed yet, and that's Math 101. So I'm going to select that. Then I'm going to erase all the outgoing edges. Okay. Okay, again, next, I'll just repeat this process. Math 102 must come next. Okay. I'm going to erase all the outgoing edges. Okay. Now we have two options. There are two vertices with no incoming edges, so we can take either one of these courses. So I'm just going to pick one and erase the outgoing edges. Okay. Now there's only one vertex that has no incoming edges, so we'll pick that one. And then erase the outgoing edges. Okay, repeat. There's only one option here, CS215. We'll erase the outgoing edges. Okay, now we can take either one of these courses. Right, there's no edges coming in, so I'll pick CS247. Cross it off the list, erase the outgoing edges. Okay, then I only have one option here, CS392. Get rid of the outgoing edges. Our last course, CS405. Okay, so if you take courses in this order, you will not violate any of the prereqs. Right? You'll have, for each one of these courses, if there is a prereq, you will be guaranteed to have had the prereq. And again, this is not the only order that someone might get through this major, but it is one total order. Okay, and that's one of the things that a graph can do for you. It can tell you these total orders, and TopSort will find not all of them, but one of them. Suppose you could write the algorithm to find all the total orders. That wouldn't be impossible. But I think I'm probably only going to ask you to find a single total order when you do your TopSort. Okay, there's another really important algorithm with graphs that we call Dijkstra's algorithm. And Dijkstra's algorithm is basically used for routing. Okay. So when we're routing on the internet, we have these machines called routers that receive packets of data, and the routers must decide where to send the packet. So when we send data on the internet, all the data is broken up into these tiny little chunks called packets, and they're sent across a series of machines until they reach their final destination. So that's basically what the internet is. It's this collection of routers where we pay an internet service provider to connect to one of these routers, and then when we have something to send, let's say we're going from A to B, we send some data, and the routers decide what's the best way to get that packet from A to B. Okay, and we rely on the internet to find a path, and it will find the optimal path, and we'll talk about how that works. Okay, let's take a little bit closer look at what a router is. Okay, so a router is a machine. It's a computer, but it's a very specialized computer, and they tend to be, at least the ones maintained by the internet service providers, they tend to be fairly expensive, specialized machines. Basically, they have these things called interfaces that allow a router to connect to many other routers. So think of these, at least theoretically, as just plugs that you can plug wires in that connect different routers together. We call them interfaces. And packets of data come in through these wires, and then the router, when it receives this packet, let's say on interface 2, it has to decide, based on the IP address of the destination, that's also included in every one of these packets. We store the IP address of where that packet is destined to go. So a router receives a packet in on an interface, and it looks up in this thing called a routing table. It says, well, where is this packet destined to go? Let's say it had this IP address. It would say, all right, to get it one step closer, we'd send it out on interface 8. Okay, so it came in on this interface. We looked up the destination IP address and decided, well, we'll get it there one step closer if we pass it out through interface 8. And that's basically, that's all these routers do, is they're pretty much 24/7 receiving packets and then forwarding them out somewhere else. And the reason this all works is because each one of the routers has a routing table. Each one of the routers knows where to forward on a piece of data or a packet to get it one step closer. Okay, and we're going to use Dijkstra's algorithm to create those routing tables. Okay, so one way to do that, one way to create these tables, is for the routers to exchange information with each other about the relative costs to communicate with each other, and then apply Dijkstra's algorithm to create the table. So the name Dijkstra's algorithm comes from a person, Edgar Dijkstra, a very famous early computer scientist. And Dijkstra's algorithm requires that a graph be created that holds the weights or relative costs to go from one vertex to another. Okay, so in a routing situation, the weights are a measure of availability. So here we have a graph where if we wanted to go from the leftmost router to the rightmost one, you see there are actually two paths that you could go down. Okay, and the question is, well, which path should, if a router receives a packet destined for this far right one, does it send it here or does it send it here? And that's what Dijkstra's algorithm does. It says, well, these routers will inform each other about things like, who has the greater bandwidth, let's say, or who has less congestion right now or in the last 5 minutes or so. That information is exchanged between all the routers, and they can come up with a relative cost. And it might be much more efficient for this router to send packets destined for this rightmost one through this path than through this path. Okay, and that's all that happens in that routing table is that little bit of information gets kind of figured out by this router, and it now sends all packets destined for this guy through this link up here. Okay, so a path with a high weight or cost should be avoided if there's another route that costs less to traverse. Now, ideally, you'd like to send your packets across the route that has the least cost. Okay, so let's talk about cost and weights. When I talk about cost or weight, I'm really talking about the same thing. Instead of storing a 1 or a 0, if we were going to use an adjacency graph to represent this, or an adjacency matrix to represent this graph, instead of storing a 1 or a 0 to represent an edge or not an edge, we can use an actual weight or cost to traverse the edge. And that number might, again, be related to the bandwidth or the congestion on the router. If there's no edge, we can choose a value representing infinity or some really high value to indicate that there's no direct connection. Okay, so here's a nice little graph. It has 5 vertices and 5 edges. Okay, what we can do is create this thing called a weight table. And the weight basically indicates the cost to go from one vertex to another. So for example, to go from 0 to 1, we go in the rows here. So from 0 to 1, we go to the column number 1, we see that there's a weight of 10. Okay. To go from 0 to 2, that's a weight of 5. To go from 1 to 4, so from 1 to 4, that's a weight of 20. From 2 to 3, 2 to 3 is a weight of 5. And from 2 to 4, there's a weight of 10. Okay, next we have to know which interface, the router needs to know which interface to forward the packet onto. And it gets this information from another table called a next hop table, or this is in effect the routing table that I talked about earlier. Okay, so let's look at the routing table. Okay, let's see if I can get this on the screen here. So what this says, if you're going from vertex 0 and you want to get to vertex 1, the next hop should be directly to vertex 1. Okay, so the way to get from 0 to 1 is to go to 1. That may seem obvious now, but if there's a cheaper cost, we'll see in a second, there's two paths to get to vertex 4. It might not be so obvious to go to a directly connected vertex to get to some final destination. But that's what the next hop table tells us basically, is you want to go from this vertex to this one. This gives you the name of the vertex that will get you one step closer. Okay, so the values in this table are locations where the packet should be sent, like I said, to get it one step closer to the final destination. Dijkstra's algorithm seeks to link disconnected vertices. So 0 and 4, for example, although they're not directly connected, okay, you can see there are at least a couple paths between 0 and 4. And Dijkstra's algorithm will find the best path, okay, or the least expensive path. And it uses the transitive nature of graphs to accomplish this. So if 0 is connected to 1 and 1 is connected to 4, therefore you can get from 0 to 4 by going through vertex 1. Right. Okay, however, notice there are more than one path, right? We could go 0, 1, 4 or 0, 2, 4. So which one should we take? Okay, and the answer, of course, is the one that results in the lowest overall cost. Okay, so we have to figure out, okay, well, to get from 0 to 1, that has a weight of 10, and to go to 1 to 4, that has a weight of 20. The sum of those two is 30. So to get from 0 to 4, taking this route, that's going to cost you 30 units. But if we look at this other path, from 0 to 2 has a weight of 5, and from 2 to 4 has a weight of 10. If we sum those two up, we get a similar bit of information. From 0 to 4, the weight is only 15. And 15, of course, is less than 30. So the optimal path, if you're going from 0 to 4, if you're at 0 and you want to go to 4, the next hop should be 2. And in fact, if we look at just a portion of the next hop table, remember this is the row is from, so we want to go from 0 to 4. The next hop, we can't go directly to 4 because we're not directly connected, but to get us one step closer, using the optimal path from 0 to 4 would be to pass the packet on to vertex 2. Okay, so in order to implement this routing in a graph, we need not only the weights, but also this next hop table. Now initially the next hop table will hold only the directly connected vertices. So let's kind of construct this weights table and next hop table. So the weights come directly from the graph. Right, so from 0 to 1 it costs 10, from 0 to 2 it costs 5, and so on. The initial next hop table will look like this. If there's a directly connected set of vertices, so 0 to 1, we'll always grab the column number. Okay, so from 2 to 4, that's the next hop is 4. From 1 to 4, the next hop is 4. Okay, so that's the initial next hop. Dijkstra's algorithm is going to find all the disconnected vertices and find the optimal or the shortest route to those. Okay, so after we apply Dijkstra's algorithm, Okay, what we're going to find out is that you can get from 0 to 3 and from 0 to 4. Okay, so for 0 to 3, right, really the only path, if you want to go from 0 to 3, is to forward the packet on to 2. Right, so that has some weight. And then we just talked about from 0 to 4, there are 2 paths, but we want to find the optimal path. Right, so where I have the stars here, these are disconnected links that go from 0 to 3 and 0 to 4. Now from 0 to 4, we said there are 2 possible paths. We could either forward the packet on to vertex 1 or to vertex 2. And we know, of course, that vertex 2 is better. That's the optimal path. And that's exactly what Dijkstra's algorithm will do for us. It will set up this table so that when we're going from 0 to 4, we know the next hop is to pass it on to 2. Okay. So let's see here. Let's talk about some actual code. The key step for Dijkstra's algorithm is finding where there's a common from and to value. Okay, so if we're going to see in a second, if I is connected to common and common is connected to j, well, what that means is there's an indirect connection between I and j. So the code I'm going to show here is a simplified version of Dijkstra's algorithm, and it's mostly pseudocode. This may need to be repeated every time we update the table. We may have to repeat this process again. There are slightly more complex versions of Dijkstra's algorithm that you wouldn't necessarily have to repeat this multiple times, but this is just the simplest example that I can show you. Okay, so we have this loop where we have a counter common is going to go from 0 to 1 minus the vertex list size. Okay, so basically common is going to span for all the vertices. Okay, but then, like I said, we're kind of going to look for cases where we have a connection between I and the common value. So the inner loop here, I, is also going to span through all the vertices. And we're going to check, basically, is there a non-infinite value between the vertices? Okay, and we can check that by just checking out the weights. Okay, so if there's a non-infinite value between weights at I common, then we know there's a link between vertex I and common. Okay, so if that's true, if weights at I common is not that special value, either 0 or infinity, well then we know there's a connection between I and common, and the next thing we'll do is we'll have another loop that's going to span from j, or from 0 to, again, the vertices. And now we're going to check to see, well, is there a link between common and j? So we can go to the weights and plug in common for the row and j for the column. And if this is true, what this means is we know there's a connection between common and j, but the only way we get here is if we know there's also a connection between I and common. Okay, so if we get in here, we know for sure there's an indirect connection from I to j. And our final step is to kind of check to see, well, is that the best, what's the best path, okay, or what's the least, the path with the least cost. So if the cost to take this route is cheaper than going directly from I to j directly, so I and j may even be connected, but there might be a less expensive path if you go around j. So what this check does here is, okay, so we know there's an indirect connection from I to j. We could check, is the cost to take this indirect path less than some other path? And if so, that's when we're going to update the weights and the next hop table, right, to reflect that there's a better way to get from I to j by again using that common vertex in the middle. So we'd update the weight, the cost to go from I to j, and we'd update the next hop table that says in order to get to j from I, you should really go through common. Common would be the hop that will get you one step closer. And like I said before, anytime you update the weights table in the simplified version, we might want to set a flag or something that says the table has changed, and we'd want to repeat this process until there have been no changes to the table. Okay, so that's the basic simplified version of Dijkstra's algorithm. And again, the idea was to look for commonality from I to common and common to j. That tells us there's an indirect link between I and j. And if the cost to get there through common is less than some other path to get from I to j, we'd update our tables. Okay, so that's the